So the Hacker Fab, I would call it sort of an initiative that we've been doing here at CMU, but it's also a course. So it's a registrar listed course that we run each semester. So I'll talk a little bit about how this is structured. And actually, these slides were from a national webinar that we did back in the fall of 24. So there's a couple things that have been updated since then, but I figure this kind of be a good launching point if you guys, want to discuss more or have some questions, right? But this is definitely something I've been pretty passionate about for, a number of years here now. So basically, this is, I said initiative we kicked off a few years ago. And this was something that we presented on a national webinar back in the fall of 24. But basically, this all originated with a guy, former student of CMU. And actually, I got to meet him when he was still in high school. So Sam Zeloof, he's been featured in Wired Magazine. He's got a pretty extensive YouTube channel. So the link to it is here. I would definitely recommend checking it out. But he essentially built a an entire working semiconductor fab in his parents' garage, collecting old equipment that was donated from companies or maybe some stuff available on eBay. And he started this as a high school student, carried through with this his entire time at CMU. We actually hired him to even work in our nano fab here for a little while, building some of this equipment. And now he has started a company called Atomic Semi out in the Bay Area. And, their goal, and this is kind of an overarching goal that we've established in the Hacker Fab, is to do sort of rapid development of chips. So they've got a ton of VC money to, bring this to reality. And I think now they're pushing up over 100 employees at Atomic Semi, and they keep growing. So this is really taken off. So yeah, if you aren't familiar with some of the stuff Sam has done, I would definitely recommend checking it out. Right. But we wanted to kind of figure out how we turn all of this into a class and sort of leverage some of the ideas that he created for this sort of DIY approach to semiconductors. Right. So the whole point of this is to try to make things more accessible. Right. So I think this fits really well into the workforce development side of things, because students can actually build their own processing equipment for a fairly low dollar amount, and they can make chips with it. I think there's quite a few things you can do with this, really, right? So the idea is that the students, it's a project-based course, and so they design either equipment or processes. Sometimes it's just software. Sometimes it's a full working process tool. But basically, they design it, they build it, and then the big thing with this is to make it open source, document it for open access, and I can share the website and everything here as well. So all of the build documents, everything that we have is on there and freely accessible. Right? So um, right. So the start of this, the picture here, this was the first semester. So this was January of 23. They started with an empty room. It's about a 600 square foot room. I'll talk about some of the facilities we have in there, but basically it was about 10 students, and their goal was to set up a fab in one semester and actually make transistors. Okay. So, again, like the whole concept here was to make this equipment affordable, create a low barrier to entry into the semiconductor space, be able to educate students, say, outside of a clean room environment. Right. So there is no clean room infrastructure needed for this, which is really one of the attractive aspects to it. Right. But we also wanted to make it easily replicable. So that's where the open source part of this comes in. And we do have students from a variety of departments. So, it's certainly weighted more towards electrical and computer engineering, but we have a lot of students from material science, mechanical engineering. We've had chemical engineering students, robotics students. I think we even had a student or two from computer science, right? So it's very much cross-disciplinary or multidisciplinary. And to be honest, a lot of these projects wouldn't work if we didn't have so many students from different backgrounds, because they basically, get separated into project teams for this effort, right? So, as I said, it is a course. So the structure looks a little bit like this. We actually offer both an undergrad and a grad section of the course simultaneously. So we have students ranging from first year all the way up through PhD. So basically every class year you could think of all participating in this at one time. And so they get projects that are basically commensurate with whatever level they're at. So even, first year students just out of high school actually they contribute a lot to this. And then, of course, people at master's or PhD level, they get a little more sophisticated project and it works. That type of collaboration has actually worked quite well. Right. Another thing that is really critical to making this run is having, well, we list TAs and here's again, sort of a snapshot of the backgrounds, but, we actually have a series of project mentors as well, typically former students that took the course and come back. And we have a mechanism where they can get research credit toward their degree by participating as a mentor in the course. Some of them just want to do it as a paid TA too, and that's fine. But we really rely on previous students being mentors for the projects. A lot of these projects are iterative too, so they basically continue from semester to semester, and things kind of keep growing as a result. Right. So again, it's very much project based and split into collaborative teams. We do lectures and labs as well. So we have basically two class periods a week. Each class period is 2 hours. But we really limit it to like 1 or 1.5 hours of lecture per week. And then the remaining time allows them to work on their projects in groups with all of us there kind of assisting if needed. In addition, we have about 6 weeks of lab modules. Originally, we actually had them building an entire NMOS transistor. So they would basically make MOSFETs across the 6 week time period. The actual MOSFET fab, by the way, is with the equipment they built. It's really like an 8 hour process. So it's not a very intensive process at all. And I could talk about that a little bit more. But basically, they do make transistors. We've kind of scaled that back a little bit now. So they're doing a lot of like doping and making resistive structures. There's a MOSCAP lab now as well. So they're building subcomponents of the MOSFET now in lab. And that's actually helped make things run a little bit more efficiently, I would say. And again, happy to, elaborate on that more. But the idea is that the lectures provide like the supporting background material that they need to know about semiconductor processing. We try to tie a lot of industry aspects into this too. So, here's what we can do in the Hacker Fab. Here's what we do in a university nanofab, but here's what industry is doing kind of on another scale, right? So we sort of, educate them on all the different aspects of this. Right. Now, the actual lab itself, I'd mentioned, was 600 square feet. So this is basically what the space looks like now. So that previous picture, you saw, just a bunch of empty boxes. In as part of that lab, we already had an existing fume hood that we use for solvents, and then another fume hood that we use for like acid and base processes. The lab's equipped with compressed air, nitrogen. We have plenty of exhaust for some of these tools. And other than that, it's just basically a series of like makers tables and benches, right? And so not a ton of stuff needed on the infrastructure front. We don't need a clean room, as I had mentioned. So it's, kind of a standard wet lab space that you'd find at a lot of universities. Okay. Now, to kick this off, that first semester in January of 23, they had a goal of making a working NMOS transistor by the end of the semester. To do that, and get this sort of off to a rapid start, they did buy initially some tabletop equipment. So they bought a little tabletop thermal evaporator. There's a little tabletop RIE, I think I have in one of the slides here. Just a few basic things to get everything going. Now, the big thing was that, you need lithography, obviously, to create patterns and really make anything. But there aren't a lot of good, cheap lithography systems that you can buy as a, kind of basic tabletop or benchtop unit, right? So the first semester really focused on establishing a lithography tool in the lab. So that was really the first DIY tool that came to fruition. And then after that, the goal was, hey, can we make everything DIY, make it for low cost? but still make it reliable and allow us to do all the processes with, sort of home built tools, right? So the first project being that stepper, actually, to spin the resist, they needed a spin coater as well. So they really kind of, developed these two things in parallel. This is actually an older version of the spin coater. They've since updated this design, but the idea was that, they pieced together the electronics, they pieced together a little touchscreen interface. Um, they have 3D printers in the lab, so basically they can make all of their own shells and mounts and everything that they need. So this entire body of the spin coater you see on the right was 3D printed, and they basically just designed it to fit the electronic units they had. The newest version, they actually use a drone motor for the spindle, right? So that's how they're getting the thousands of RPMs needed to spin the resist. Very basic little vacuum chuck included, and a little diaphragm pump just to hold the chip onto the spindle, and it works quite well. So the latest version of this, you build a spinner for $100, extremely cheap. Right now, the lithography system a little bit different. So the first version of this, they started with an optical projector, and isolated certain wavelengths out of that. They built this little like cantilever arm that you see here, basically coming off the front with the optics needed to transfer the image. So basically, it is a direct write lithography system, but it's more of like a projection scanner. So basically, they can just take any pattern and send it to the tool via HDMI, right? So you could have your CAD file, directly open, or you could save it as a bitmap image, or even a PowerPoint slide. Technically, you could take and expose onto the chip. So very versatile. Don't need masks. You can really create any type of design that you want. And so, it basically kicked things off and got things going very well, but it did have its issues. And, this whole assembly being cantilevered off the front of this projector, it leads to a lot of instability, definitely vibration sensitive, things like that. So as I mentioned, a lot of these projects are iterative. So basically they sought to, make improvements on the stepper. And so this is basically what we're calling version 2. There's actually a version 3 now that I probably should have updated this with. And I have the pictures of it if you guys want to see it. But basically, they bought a DLP chipset from Texas Instruments, and a FLIR camera to image the wafers. They put some improved optics in, and they basically, took like a near UV LED, so basically 405 nanometer LED, and connected that to the drivers, and basically now have a really nice, much more stable lithography tool. And we get about 2 micron resolution out of this. And they've actually since improved the alignment accuracy. They've since built a better stage with closed loop control and micro positioners that are all automated via stepper motors. And they've actually 3D printed, all the mounts for that as well. And again, all these plans are online, so anybody can build this, and it's worked quite well. And so actually, the current version of the stepper that's online, you can build a lithography system now for $3,000. And again, all those plans, including the bill of materials, the build documents, the standard operating procedures, even the software that runs it, because they developed their own GUI to drive all of this. Everything is available online. The software can be downloaded for free as well. And we've had some other labs on campus, and a number of other universities have now replicated this as well. So it's a very low cost, efficient way to be able to introduce lithography into, a class or a lab type setting. Right? Since then, they had built a little thermal evaporator. So this was a really cool device that, of course, the turbo pump is expensive. But otherwise, we use these little cube type vacuum chambers. from ideal vacuum. So you could put together a vacuum chamber for, in some cases $1,000 or maybe a couple $1,000. It depends on what port you want and or how many ports you want, what types of ports, size of the chamber, and so on. But you can get these little 6 by 6 inch, 9 by 9 inch, 12 by 12 inch type chambers for very cheap, right? And they basically create the little cheap DC power supply off of Amazon, and they were able to basically build this to hold a little tungsten filament and works quite well. So they actually evaporate aluminum in this thing pretty regularly, and we actually use it for the lab modules of the class, not just for the DIY aspect. We actually use it as a class tool, right? So as of right now, and actually I should have updated this ahead of this talk, and I have a couple other slides I can pull up if you guys are interested. But basically, they've got a spin coater working. Since then, they bought these really cool tiny little hot plates. I can get the brand if anybody's interested, but they've built some hot plates. They've built a obviously the maskless lithography scanner that I just showed you. There is a tabletop tube furnace that we use a lot for doping. So we do doping via spin on glass, right? So we buy from Filmtronics the either boron or phosphorus doped spin on glass. That's how we can create the N wells or P wells on the transistors. So works quite well. We have a little tabletop RIE. So everything in bold, by the way, denotes something that has been built via DIY. All right, so I already just showed you the thermal evaporator, and then of course we have just some basic optical microscopes. They have been working on developing like a fully automated test station, basically a probe station. So that's under development. Um, we've got the 3D printers, like I mentioned. So this list is actually now much more extended too, because we have projects going on. They're building a 2D chip stacking robot at the moment, so we can basically take different 2D materials and stack them in an automated way. There was a scanning probe microscope that was constructed. Um, Actually, we are about to try to deposit our first films in an ALD that has been going on for like I think 3 semesters. So as early as possibly next week, actually, we might be trying to deposit some hafnium oxide films in that structure or in that tool. And then we have a working sputtering system. And again, I could show you some more images of all that stuff. The sputtering system is extremely cool because they completely designed the chamber, custom designed cathodes that are air cooled instead of water cooled. I mean, they really went all out with this thing. And then RF sources are, quite expensive. So they actually figured out how to use a ham radio and an antenna tuner as their RF power source. So basically that can put out 14 megahertz with up to 100 watts of power. And these are little 2-inch targets in the sputtering system. So plenty of power. And they're doing both metal deposition and reactive deposition of, say, like aluminum oxide or other oxide films. With part of the goal being they want to actually develop a PMOS process so we can do CMOS devices. Because right now our standard process that I'll show you here is just for NMOS, right? But in the early semesters here, basically they focused on like developing the litho capability, the spin-on doping and diffusion processes, some wet etching processes for the transistor, the thermal evaporator that I'd shown you, a little bit of basic metrology. And, after putting all this together, they actually have fabricated working devices. So basically, as I mentioned, it's about 8 hours to make a full NMOS transistor. And if you look at the image here, basically, you see these bigger dark pads are your contact pads. These, if you can see my cursor, the line extending out here, that is the gate. So this long linear structure that you can kind of see in the background, that's the channel, right? So we have a source pad, a drain pad. We've got the gate extending across the channel here. Those are aluminum gates. And we've got basically the contact pad to supply the gate voltage. So you can see from the IV curve, they actually do they do function as a transistor. And we've actually made some improvements on it since then. So this example was basically like a 2 micron gate length. It's a self-aligned process. Again, these are NMOS devices, and all the contacts are aluminum, right? So they've done this now pretty much, except for I'd say like the RIE and the tube furnace for the doping. Every aspect of this otherwise has been done with the DIY equipment, right? So, again, this was a little bit of an older presentation, but like moving forward, some of this has already either been developed or in development. So we have a team right now that's working on like developing CMOS processes. We're trying to look at a lot more emerging devices. We want to tie this in with the broader research community too, to keep everything relevant, right? So we haven't done this yet, but we may try to look at building some basic memory devices or some biomedical type structures. Possibly integrate some photonics devices. So actually, we were just getting some SU8 together earlier today. They're going to try to make some waveguide structures out of SU8 coming up. So trying to push forward on that. And then we're also trying to bring like automation and things like digital twins and AI into the fold as well. All right. So trying to collect data from these tools and use it to maybe develop some AI models, right? So there's been a lot of interest on that front. Um, but as I said, like sputtering is already online, atomic layer deposition, hopefully very soon, and like various robotics projects like the 2D material stacking. And we actually tried to even do like automated spin coating and baking robots as well. Got a little headway with that, and then that project kind of ended just due to lack of people on it. But might be something that we bring kind of back into the fold, right? Um, so, uh, again, this is a little bit older, but you can see they've updated the software for the stepper. That's another big thing that's been ongoing. So they've now actually been able to do pattern recognition and add automated alignment features to the software. I had mentioned the closed loop control already for the stage. They are working on how to do like tiling and stitching of patterns so that we can do larger exposure areas. Because right now the total field size is just limited to less than a couple millimeters. But in theory, for bigger structures, we can tile things together, and so they've been working on that for about a semester and a half. Um, and this is an older version, or older picture of the sputtering system, but I can certainly show you the more recent version. Actually, the whole thing is on the website now. Um, so we started the course with like 10 to 20 students, um, and now we've scaled it. Or actually, we started with 10 students, and now we've actually scaled this. This said 10 to 20. Last semester we actually had 34 students. This semester we've got about 26. So we certainly scaled this up quite a bit. It does run every semester, actually, and we even have students working there in the summer. So this is kind of a year-round project. The big thing is, as I mentioned earlier, like the TAs and the project mentors, right? So we need a good team of them to really make this work. So there's two of us that act as co-instructors for the class, overseeing everything, giving lectures, participating to some degree in the lab, but it's really a lot of those students that are driving this and keeping it going, right? So we're hoping, future semesters we even scale this up to 40 or more students. We've already seen at least 4 to 5 departments involved. And we've had some industry sponsors participate as well. So there was money from like Apple and Intel to kind of help kick some of this off. So and again, the big thing is the open source concept. So the links to the websites that house everything are in here. So all the open source material, we have a Git book and a GitHub page that lists all of that, and I'm happy to show you the website here. But basically, if you just Google CMU Hacker Fab, it'll take you to the website, and then you can click on the links to get to the GitHub information. You may also recognize that the FabuBlocks diagrams here. So we do have processes available. The full like 45 step NMOS process is available on FabuBlocks. I can't remember if I shared that with this group because I know that Jan had set up a folder for us, but that may be in there. And then actually another big aspect of this too that I didn't mention is it says open discussions on Discord. So Discord, we're pushing up to like 3,000 people on Discord. So this has actually gone international. So there's a Hacker Fab in India, a Hacker Fab in Poland. There's a Hacker Fab at Waterloo in Canada, and several other U.S. universities. So a lot of the students participate in open discussions on Discord to share ideas and figure out how to hack things. And we have high school students on there as well, and just people that are general kind of hobbyists that are interested in this stuff. So it's really kind of taken off in a lot of ways, right? So, we have helped people replicate this idea. So if people want to recreate it, obviously the open source aspect is extremely important. And so you just basically need a little bit of lab space, ideally something that can handle the chemicals, right? So you need some level of exhaust. And we do work closely with environmental health and safety on this to make sure that we are doing all of this in a safe way. And that relationship has gone very well. So it's really been, knock on wood here, no issues. But yeah, it's starting to really kind of take off. And, we're looking ideally to get some more industrial engagement and corporate sponsorship. We try to bring guest lectures in as well, to, talk about specific, either industry aspects or things that we don't typically cover, like our department head for material science has given a guest lecture on characterization and metrology a few times. And so, we try to bring a little bit of industrial flavor and teach them about some other things. We've had some packaging lectures and everything as well. So the real key though is the students and they actually we try not to call it a club, but they actually kind of view it in a way as a club, and we've had a number of them say it's their most favorite course, since they've been at CMU. So, I mean, it's really kind of taken off. So that's the gist of it.